Hi, and welcome to this video on organic and inorganic compounds. Today we're going to look at both the historical and contemporary definitions and introduce some examples of each along the way. The initial classification of organic and inorganic compounds was made centuries ago, but has since changed. In awe of living organisms, early scientists theorized that there must be a fundamental difference between living and non-living things. This was rooted in the theory of vitalism, which held that living organisms were driven by a vital force, which made them inherently different from their inanimate counterparts. Thus, vitalist scientists categorized the chemical compounds of living organisms as organic and the compounds of non-living things as inorganic. Believing that humans could not make or manipulate the vital force of living organisms, chemists believed it impossible to synthesize organic substances from lifeless inorganic compounds. It wasn't until the early 1800s that chemists debunked this vitalist theory. Friedrich Wöhler synthesized urea, the primary nitrogen-containing compound in urine, and thus an organic compound, using potassium cyanate and ammonium chloride, two inorganic compounds. In doing so, he demonstrated that no vital force fundamentally separated organic from inorganic compounds, and that the latter could be used to make the former. However, while vitalism was thoroughly debunked, the nomenclature of organic and inorganic lives on in modern chemistry, but with updated definitions. Broadly, by today's definition, organic compounds are carbon-based substances. This is actually in keeping with the initial vitalist definition because terrestrial life forms are in fact carbon-based. Consequently, most of the chemical compounds in organisms are organic by today's definition. For example, DNA, proteins, fats, and carbohydrates are all organic compounds. However, unlike the vitalist definition, organic compounds do not have to be derived from a living organism, but can be synthesized in the lab. For example, nylon, a useful and popular polymer, is a synthetically manufactured organic compound. From simple carbon chains, called alkanes, saturated with only hydrogen, to long, complex molecules full of various functional groups, there are millions of organic compounds. Functional groups are comprised of the elements in the top right corner of the periodic table: oxygen, nitrogen, sulfur, phosphorus, silicon, and the halogens. Organic compounds are typically molecular solids, meaning they form self-contained molecular units through covalent bonding. In the solid and liquid phase, these units are held together by weak intermolecular interactions, which leads to lower melting and boiling points compared to many inorganic compounds. Inorganic compounds can generally be defined as compounds that are non-carbon based. This obviously encompasses a large part of the periodic table, so the physical traits of inorganic compounds vary drastically and are hard to summarize. We encounter lots of inorganic compounds daily. For example, ionic compounds like sodium chloride, the quartz in your watch, which is silicon dioxide, and water, the most well-known inorganic compound. Maybe at this point, you're thinking to yourself, well, if there's carbon in the compound, I'll consider it organic. Unfortunately, while all organic compounds contain carbon, not all carbon-containing compounds are organic. For example, alloys that contain carbon are considered inorganic. This includes steel, an alloy of iron and carbon. And allotropes of carbon, like graphite and diamond, are not considered organic compounds because they are simply one element, not a compound of elements. Additionally, simple oxides like carbon monoxide and carbon dioxide are often defined as inorganic as well. This may actually be a holdover from vitalism, which considered carbon dioxide inorganic because it was produced by inanimate sources like volcanoes and minerals. Thus, a stricter and perhaps more useful definition of organic compounds requires the compound to have carbon-hydrogen bonds. Although even this definition has notable exceptions, like urea and carbon tetrachloride, which do not contain carbon-hydrogen bonds but are considered organic. Furthermore, some organic compounds form complexes with metals, which are typically the focus of inorganic chemists. This gives rise to intermediate classifications, like organometallics and metalloproteins. Here, in heme, the metalloprotein and hemoglobin, you can see an organic structure centered around an iron atom. If all of this felt, well, a touch arbitrary, that's understandable. There really aren't perfect definitions for organic and inorganic compounds. Even IUPAC does not provide specific definitions. However, with that being said, it is still practical to acknowledge a difference between organic and inorganic substances. The chemistry of organic and inorganic compounds is so different that it makes sense to teach them separately and for chemists to specialize in one or the other. For example, the behavior of larger metal atoms can be quite different from the smaller atoms in organic compounds, and the synthetic techniques used to build complex organic molecules require deep expertise that may not be relevant to inorganic chemists. So while there are some ambiguities in the definitions, it is useful to have a general understanding of which compounds are organic and which are inorganic, because of the chemical knowledge required to understand each class. Finally, take a second to look around you. Pick a few objects and decide if they would be considered organic or inorganic. Consider if they were derived from organisms, are ionic compounds, or contain metal. LCD screens have layers of silicon dioxide. Are you sitting at a wooden table? That wood is made up of complex organic compounds. To get better at classifying compounds as organic or inorganic, consider a few objects around you every day. Thanks for watching and happy studying.